Let us look at proposition number 112 of book 10 of Euclid's Elements. The proposition says the square on a rational straight line, if applied to the binomial straight line, produces a breadth and apotome, the terms of which are commensurable with the terms of the binomial straight line, and moreover in the same ratio, and further the apotome so arising has the same order as the binomial straight line. So let's see how we can prove that. Let A be a rational straight line, BC be a binomial. What the proposition is saying is that if we apply the square on A to BC, then a breadth is produced, that is FE is an apotome and BC a binomial. So FE is the breadth that is produced by applying square on A to BC, and the terms of FE, that is FK and KE, are commensurable with the terms of CD and BD of BC. And not only that, they are in the same ratio and it has the same order as BC. Divide BC into its terms BD and CD such that CD is greater than BD. Now remember, since this is a binomial, that means CD and BD are commensurable in square only. Okay. Now we find EF such that BC by EF is equal to A square on A. Now we find G such that BD by G is equal to A square. So now both of them are A square. So which means they are equal to each other, that is BC by EF is equal to BD by G, which implies BC is to BD as G is to EF. And since BC is greater than BD, that means G is also greater than EF. Okay. Now we extend EF to H such that EH is equal to G, so that our proportionality becomes BC is to BD is equal to EH is to EF. Taken separately, we can say CD is to BD is equal to FH is to FE. We take KE such that FH is to FE is equal to FK is to KE, which implies HK is to FK is equal to FK is to KE. Now, since FK is to KE is equal to CD is to BD, HK is to FK, HK is to FK is equal to CD is to BD. And we know CD square is commensurable with BD square because they are commensurable in square only. That means HK square on HK is also commensurable with the square on FK. See here, HK is to FK equal to FK is to KE. That means HK, FK and KE are in continued proportion, which implies HK square is to FK square is equal to HK is to KE. HK square is commensurable with FK square. That means HK is also commensurable with KE. That means EH is also commensurable in length with KE. How did this come? HK is commensurable with KE. That means the whole is commensurable with a part. That means the parts are commensurable with each other. So that is how EH is also commensurable in length with KE. Now, A square is equal to EH by BD. Here we have A square is equal to BD by G. But G is equal to EH. So we can say A square is equal to EH by BD since EH equal to G. And A is rational. That means the square on A is rational. That means EH by BD is also rational. Now, if the area is rational and it is bounded by or it contains or it is contained by a rational and another line, that other line will also be rational. So EH by BD is applied to BD, a rational straight line, which implies EH is rational and commensurable in length with BD. Since EH is rational and BD is also rational, we can say they are rational and commensurable in length. Now, KE is rational and commensurable in length with BD because EH and KE are commensurable with each other. And since EH is commensurable with BD, KE is also commensurable with BD. Okay, now CD is to BD is equal to FK is to KE. Where is that? CD is to BD equal to FK is to KE. And we know CD and BD are commensurable in square only. That means FK and KE are also commensurable in square only. And since KE is rational, so is FK. So we have FK and KE are rational and commensurable in square only, which means FK minus KE, that is EF, is an apotome. The square on CD is greater than square on BD by the square on a straight line, either commensurable or incommensurable in length with CD. This is from the fact that BC is a binomial and CD and BD are its terms. And because of this proportionality, so we have two options. Either it is commensurable or incommensurable in length with CD. So let's take it one by one. If commensurable, CD square is greater than BD square by the square on a straight line, commensurable in length with CD. Because of this proportionality, we can say that FK square is greater than KE square by the square on a straight line, commensurable in length with FK. Now, if CD is commensurable with a rational straight line set out, so is FK. If BD is commensurable with rational straight line set out, so is KE. And if CD and BD are incommensurable with rational straight line set out, so are FK and KE. All this is because of this proportionality. So whatever are the properties of CD and BD, same will be for FK and KE. Now, if it is incommensurable, that is CD square is greater than BD square by the square on a straight line, incommensurable in length with CD, then FK square is greater than KE square by the square on a straight line, incommensurable in length with FK. And if CD is commensurable with rational straight line set out, so is FK. If BD is commensurable with rational straight line set out, so is FK. And if CD and BD are incommensurable with rational straight line set out, so are FK and KE. So now based on whatever we have now, we can say EF is an apotome, BC is a binomial we are given, and we have these terms of the apotome FE, FK and KE of an apotome, and they are commensurable with the term CD and BD, which are the terms of the binomial straight line BC. And they are in the same ratio and it has the same order. So we have shown what was required. That if we apply the square on a rational straight line to a binomial, then it produces as breadth an apotome such that the terms of the apotome are commensurable with the terms of the binomial straight line. and they are in the same ratio, and they have the same order. So that is proposition number 112 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.